Again, you might want your formula sheet handy just so you can kind of, again, see where those equations are. Alrighty. Imagine that you're in a car turning a corner, going in a circle. What's the direction of your acceleration? And what's the direction of the force that acts upon you? What's the direction of your acceleration? Inwards, towards the center. Now, can I give you some advice? You may have noticed these questions appear quite often on your test, where there's a chart with two options to pick from, and then A, B, and C. The best way to solve these is not to read the correct answer. That's the dumbest way to solve them. The best way to solve these is to go vertically through each chart. So again, which way is the acceleration, folks? Go like this, and I want all of you to do this. Go down the acceleration column, put a check mark, put a check mark, put an X, put an X. If you want to, you could even now cross out C and D because you just put an X in that row. So the acceleration is inwards. What direction is the force? Why is the force also inwards? Because acceleration is where force gets its vector from. So the net force is going to be inwards, no, and now I can zoom out and I see clearly it has to be A. I do it that way because I've long since lost track of how many times, Julie, I've thought the right answer and circled the wrong letter because just reading back and forth, I got the columns mixed up or something dumb like that. So I strongly advise doing this method. You will see, I guarantee, on every test for the rest of the year, a multiple choice question like this, where I ask you a conceptual question, and I give you two columns. In fact, I think you've seen one on every test so far this year. It says, explain your answer using relevant principle of physics. Well, really, the reason the force is towards the center is because the acceleration is towards the center. Why is the acceleration towards the center? We actually, 2 lessons ago, did some vector subtraction to prove it. But you know what? An easier, more intuitive way, I've taught you starting last year that our bodies are backwards accelerometers. We feel acceleration backwards. So, if you go around a corner and you feel like you're getting pushed outwards, which way are you accelerating? Inwards. Okay. So I'm not going to do an explanation. Instead, let's do some calculating. A car is approaching a circular turn that has a radius of 60 meters. If the coefficient of friction between the car and the pavement is 0.45, what's the maximum speed that the car can safely travel through the turn? There's a bit of a problem here, and part of the problem is how do we DULP? How do we draw this? How do we do a free body diagram? If I do a top view, don't write this down, if I do a top view, I would have this. Car. And I would say to myself, what are the forces, if this is top view, what are the forces acting on this car? Get the obvious one. Which way? This way? No. Oh. So in this case, a top view doesn't do us much good. A front view does better, but even that is a bit tricky. So I'm going to show you how I draw these. We're going to be going around a corner in a circle. I think the first thing I'm going to do is I'm going to draw the center of the circle. I usually just draw a little pole right there. I'm going to draw a road. There's the road. I'm going to draw the car coming towards us. Now, this is Mr. Duick's stick art. You can do this better if you want, but typically I draw a little rectangle. I put 2 headlights so that I know it's coming towards me. I put 2 little rectangles for tires and a roof. Now, even that is horrible. Even this is horrible. So to add a directional component, what I'll typically do, Kayla, is I'll draw an arrow like that. That's meant to show that it's coming out of the page towards me, and it's going to be going around the corner that way. You can come up with your own system, and those of you that are more artistic can add a nice 3-dimensional component to the car. You can kind of, make it 3. I can't do any of that. I'm not going to bother doing any of that. This works for me. In fact, you know what? There may even come a point when I don't even draw the car. I'll represent its mass with a little dot. But for now, there's the car. I tend to still put the headlights on. It just reminds me it's coming towards me. I like to think even with my hideous drawing, this is at least vaguely intelligible. And so now I say to you, what are the forces acting on this car? Get the obvious one. Which way? See, now I can draw it in properly. Is the car sinking into the ground like quicksand? Is it flying into the air like Superman? So, what else? And I think the normal force is going to be exactly the same size as mg. Is that okay so far? And now we bring in this unit. What path is this car tracing out? A circle. So there must be an unbalanced force pointing toward the... I draw that force in. I know it's there. I don't label it FC. Drake, FC does not appear in my free body diagram. It's going to appear in my equation. Here's the question. What force pushes a car around a circle? And you would have hopefully experienced that with all the snow that we've been having the last couple of weeks. Robbie? Yeah. Okay. There's my setup. From here, it's going to be actually kind of clean, almost physics 11, but with centripetal force. Because now I would say to you, vertically, who's winning? It's a tie, so who cares? Horizontally, who's winning? Toward the center. So what force is towards the center? Do I have any forces pointing away from the center? No, and again, this is what I've tried to convince you. There is no force pushing you out. What you feel pushing you out is actually your body's own inertia, wanting to keep going in a straight line at a steady speed, but inertia is mass. It's not a force. What does that always equal? In physics 11, it was always F net. It was always MA. In physics 12, in the first forces unit that we did, it was still MA. Are we moving in a circle? Well, then it's going to be MAC. The most common mistake, kids forget the mass. And the reason they forget the mass is the acceleration equations, James, in this unit are so complicated that they think it contains a mass. No. So I go like that. Now, on your formula sheet, and please make sure you know where these are. James, there's two circular acceleration equations. Can you read them to me? On your formula sheet, under centripetal force, there are two acceleration equations. Yes, I'm testing to see if you know where they are. And what else does it equal? I got the v squared over r, Captain Obvious. Next. It also equals... You might just want to jot that down just to jog your memory. Which one of these am I going to plug in for the acceleration? It depends whether this question is mentioning speed or period. If it asked how long to go around the corner, period. What does this question want me to find? See it, James? Maximum speed. So I'm going to use this equation. My next line is going to look like this. mv squared over r. On the left-hand side, friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one? We're not on a ramp. We're not on a slant. It's good old physics 11 now. So I get this. Mu mg equals mv squared over r. Do we have to build separate roads for semi-trucks and logging trucks and buses and little tiny cars? Do we have to build separate roads for them? Do you know why we don't have to build separate roads for them? Now, let's pause. Don't write this down. We are assuming that the center of mass is right at ground level. It is true because buses and logging trucks have a higher center of mass, that they are more tippy than small little cars. So I'm fibbing a little bit. They can't all go on the same roads, but you can't drive them exactly the same because I have dramatically simplified where the center of mass is located. Okay, so should you become a logging truck driver, please don't think to yourself, oh, Duick says the mass cancels, I can do that corner the same way the Porsche did. No, no. But in our magic physics world where we're keeping everything simple and treating everything like it's the same shape, like a box, yes. Okay. What did this want me to find? Oh, how would I get the V by itself? You know what? This is almost like yesterday. This is Muger, square root. They gave me the coefficient of friction, 0.45. And if you're wondering, you've all seen when you approach a corner, there's always a road sign with a speed limit. This is how they calculate it, although I expect they also build in a big safety margin. 9.8, because it has to be able to work in all weather. And so the coefficient of friction would change when it's raining. They don't want you to wipe out when it's raining. What was the radius? 60? You okay there, Connor? Good, shut up. Here we go. Square root of that. 16.26 in kilometers per hour. This is a nice, wide, good corner. You could do this at road speed. This would be a corner that doesn't probably have a speed limit sign posted. This would be just a banking kind of a road. Now, we also tend to angle or bank roads, putting them on ramps. We may look at that later, but I've flogged ramps in the forces unit, and I'm cutting, no pun intended, corners. I'm trying to get some shortcuts along the way. I wish I had made that pun up, because that was a glorious pun, by the way, cutting corners. I may skip that. So anyways, 16.3 meters per second. I do like this question. I like this question. I like this question in that this is a nice example of, here's a nice application of centripetal force. And you know what? It's a nice engineering puzzle. Hey, how fast can we go around the corner safely? Example 2. A test tube rotates with a period of 9.9 times 10 to the negative 4 seconds. It rotates every 0.00099 seconds. It rotates really fast. Now, these spinning test tubes are called centrifuges. They really should be called centripetas, because centrifugal force isn't a force. Although, really what they're doing is they're using the own inertia of the masses to separate the masses. Okay, anyways. What is the centripetal force on an amoeba at the bottom of the test tube? The bottom of the test tube rotates in a circle with radius 0.17 or 0.15. You might be saying, Mr. Duick, this looks slanty. While the test tube is slanty, I think the circle that we're translating out is exactly dead horizontal. What does this question want me to find? Which force? Centripetal force. You know what? I think I don't need to go all free body or anything like that. I think I can go straight plug and chug. I can say FC equals M AC. James, remember, there are two expressions for circular acceleration. There's that one, and there's this one. Which one am I going to use here? It always depends on what they ask for or what they give me. Did they ask for or give me speed, or did they ask for or give me period? See it, Drake? They gave me the period. I'm going to use this one. Right there. You okay with that? No? Okay. Have you got your formula sheet? You see the formula sheet? You see the two different equations? Okay. So, period, that's the T. That's the symbol for period. V, hey, what's that a symbol for? You know that already. This time, technically speed, because the direction's always changing. But yeah, I'll take velocity. Here, they didn't mention a velocity. They talked about a period. I'm going to use this equation. It's still ma, but I'm going to use this acceleration, not this acceleration. In fact, on my next line, Drake, I'm going to write this. You know what? Not on my next. Yeah, I got room. The centripetal force is m4 pi squared r over t squared. Drake, do a quick check. Did they give me the mass? Yep. Did they give me the radius? Yep. Did they give me the period in seconds? Straight plug and chug, no free body diagram necessary here. What was the mass? It was really small. 1.8 times 10 to the negative 9. 4. I want all of you to try this because some of you on your calculator might get an error. Period is 9.9 times 10 to the negative 4. Every one of you, I insist that you try this on your calculator. Where you might get an error, you might not be allowed to type pi squared on your calculator. Some of your calculators might require you to go pi times pi. So try this on your calculator. I'm not going to move on until I see everybody typing on their calculator. Oh, I missed the radius, Mr. Duke. Dope. Ah. Ah, jeez. Times 4 times pi squared times 0.15 divided by 9.9 times 10 to the negative 4 squared. I think you'll get 0.010875, that there. Okay, let me pause the video for a second. So I got 0.0109. If I go to 3 sig figs, 0109 units. It's a force. Newtons. Cool. Lindsay, what does example 3 want me to find? Centripetal force. Now, these are the, I think the ride at Playland, is it called the wave swinger? The swings, okay? Now, even though the rope is out at an angle, please notice, the circle is a nice horizontal circle. We don't need to go all funky here. Lindsay, what does it want us to find? Well, centripetal force is going to be m times centripetal acceleration. No free body diagram here required. There's 2 equations for centripetal acceleration. There's the v squared over r, and there's the 4 pi squared r over t squared. Hey folks, which one am I going to use here? This is a trickier one. Why am I going to use the v squared over r? Max? They gave me kinetic energy. Oh, and that has a v in it. Yes? Okay, so you see how we're putting stuff together? Okay. So on my next line, I'm going to write Fc equals mv squared over r. I know my approach. Now I'm going to go take that kinetic energy. Now that kinetic energy is equal to a half mv squared. Okay. I was going to get the v by itself, but look up. Since this is a v squared and this is a v squared, instead of getting the v by itself, why don't I get the v squared by itself, and then I can replace the v squared with the v squared. It's going to be less work. Is that okay, James? Yeah. So I'm going to, I guess, times by 2 and divide by the mass. That's the v squared in kinetic energy. And last unit, or a couple units ago, to find v, we would have actually taken the square root, but I'm going to say, why bother in this case? I can plug this in right to there. When I do that, I'm going to get the centripetal force is equal to, there's going to be an m. Robbie, you ready? I drew my fraction bar. The 2 is going to be on the top. The KE is going to be on the top. Looks like the M is going to be on the bottom when I replace the V squared with that fraction. Brandon, did I lose you? Suddenly coughing again. How many of you been on the wave swinger before? The swings. Okay? If a swing is empty, will it swing out higher, lower, or just the same angle as a swing that's occupied? What? Same angle. Why? Okay. Now, it's actually not quite true. Human beings have a bit more air resistance than an empty swing, and so an empty swing will swing out a tiny bit higher. In our magic physics world, we're making things easier. So, the centripetal force is equal to 2. What was the kinetic energy? I've scrolled down. Divided by 7. I can almost do this in my head. Two times 460 divided by 7. 131 newtons. Okay? Don't turn the page yet. What path is this swing tracing out? So where must the net force be pointing? Over here, I don't know how you have yours set up. I've got room in the bottom corner. Draw somewhere, if you can, on this page, draw a little square. It's a cool free body diagram. Here's the swing. What are the forces acting on that swing? Get the obvious one. What else? Don't say circular force. It's not going to show up on my picture. What else? The chain. Oh, what? Tension, up at an angle. Did I say angle? We could componentize this, but instead, I have, those are the only two forces acting on it. I do have two vectors. Why don't I just combine them, add them together, as it were? How might I add them together? Draw them. So, if I draw mg plus tension, can you see the resultant is horizontally towards the center, like I told you. Isn't that nice? I didn't fib. When you're moving in a circle, what direction is your net force always? Toward the center. Oh, and I knew to stop drawing tension, Simone, right there, because I know the net force is horizontally towards the center, because it's a horizontal circle. If you gave me theta and a bit more information, I could do all sorts of neat stuff. Preview of coming attractions. I like example 4, I like example 4, I like example 4. Why would I say that, Riley? Did you hear me say that? You're the kind of teacher, you're a student that tends to notice when your teacher emphasizes certain things? Okay. This, by the way, also because this is good physics, because all of you are still stupid drivers. Typically the males, but not always the males, think, oh, it's all about my driving ability. I can overcome the rain. No. So it says this, a car can travel without slipping at a maximum speed of 32 meters per second in a circular path of radius 72 on a dry horizontal surface. By the way, this is going around a corner at about 100 kilometers per hour. This is a sports car. When it rains, the coefficient of friction is reduced to 1/2 its original value. What's the maximum safe speed of the car under this wet condition? You know, I think before I even jump on in, I'm sensing this question has two conditions. What are the two conditions? Give you a hint. The second one starts with the letter W. Okay, I think I'm going to divide my page into halves. And you know what, Connor? I'll call this side the dry page, this side the raining wet page. Okay? Let's draw a free body diagram for the wet. Okay? This is a car going around a corner. That's how we opened up today's lesson. Remember what I said the best way to draw it was? Not from a top view, James. Instead, give yourself, this is the center that we're going around. We're going around like that. Put in a road, and this is Mr. Dewick's handy-dandy schmandy little diagram. Car headlights coming towards me. Nikki, what are the forces acting on this car? Get the obvious one, Nikki.
MG.
What else? Same size as mg because we're not slanted. And what else? I know there has to be a force pointing that way because we're going around in a, looking for word begins with letter C, circle. What force pushes a car around a circle? Okay. I think the free body diagram for the dry road will be identical. What's going to change between the two of them? Only, huh? I got to be fussy. Technically not friction, technically some subpart of friction. What's going to change between the two of them? The coefficient of friction. Let's continue going on the wet side, though. So who's winning? Vertically, Michaela, it's a tie. Horizontally, we would say friction is what's pushing me in a circle. Friction is mu times the normal force. Centripetal force is mass times AC. Which version of the acceleration am I going to use? The one with the period or the one with the speed in it? So I'm going to use mv squared over r. And friction is mu times, I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force. And in fact, Tori, what we just did is we re-derived the expression we had from the first example. I think we're going to find the maximum safe speed is the square root of mu times g. Do I know g? 9.8. Do I know r? 72. Do I know mu, the coefficient of friction? All I know is that it's half, is it half or 1/4? Half of its original value. I guess now, Julie, we better go walking over to the dry side. I think the dry side is going to have the same FBD. In fact, it's going to have the same equation. Except, what do I find? What do I want to find on the dry side? Yeah, I want to find the coefficient of friction, mu. And then I'll just divide it by 2, and I've got the number for the other side. You okay with that, James? So I think we're going to end up with mu mg equals mv squared over r. Once again, the mass cancels. But what do I want to find? I want to get the mu by itself. So I guess it's going to be v squared over gr. How fast can I go when it's dry? They gave me the speed, did they not, I think? How fast is it? 32? Divided by 9.8 times, was the radius 72? (32) squared divided by bracket 9.8 times 72. When it's dry, I get a really high coefficient of friction. These are good dragster tires. I really should change this number and make it a bit more realistic. But, well, no, you know what? I mean, the corner has a radius of 72, which is about 3/4 of the football field. So imagine that. Imagine a corner with that radius. You're doing it at about 120 clicks. Okay, you got to have some good tires to do that. So, I mean, based on the numbers that I made up, this answer doesn't surprise me. I just don't like coefficients of friction bigger than 1. They creep me out. But wait a minute. So I'm going to write 1.45. Units for mu? No. Now, I want half of that. Divide by 2. Okay. So the mu over here, I'll call it mu when it's wet, is point, what was it? 7256. The reason, what I mean by I like this question, by the way, this is a good multi-step question that really tests your understanding, and hopefully you're cluing in that it has nothing to do with driving skill. It's physics. Slow down when it rains, especially in the snow. Any of you do any driving during the snow days at all? Any of you, while you were carefully driving, have some idiot go zipping past you at like 85 clicks? That's what, it's not, like I'm a very cautious driver. That's not what scares me when it's snowing. It's the people that aren't cautious because they're going to take me with them, right? Drive smart. Drive physics-ish. Square root of, I'm going to put the 0.7256 in there. I'll use my answer button. 9.8, 72. Quick like a bunny. $22.6. Is that right? Now, this is a very counterintuitive question. A lot of people will say, well, if you only have half the traction, you can only go half the speed. Nope. We didn't get an answer of 16. It's because of the squareds and the square roots and all sorts of stuff in there. Okay. 22.6. Ready for a bit of technical comment here? So the reason that friction is inwards has to do with how your tires work. When you turn your front wheels to the left, the car wants to keep going in a straight line at a steady speed. That's Newton's first. But because you've turned your tires to the left, they apply a force against the road that way. Forces come in pairs. The road applies a force against the tires that way. Okay. Oh, and if friction can't apply a big enough force, Newton's first will kick in, and you're going to overshoot the corner and end up in the ditch on the outside of the corner. Hopefully none of you experienced that. Okay. Let's go into outer space. Another application of this, Nevada, would be artificial gravity. If you want to induce artificial gravity in outer space, one way would be to build a circular space station and then spin it. Now, there's some problems with that method too, which I'll talk about, but for now, sure. Suppose we built a space station and it has a radius of 30 meters. What does the period of rotation need to be for an astronaut to experience 80% of Earth's gravitational field? What if we want fake gravity to be 80%? Cool. You know what this is a job for, Rebecca? Free body diagram. I would normally draw it myself, but they gave me lovely pictures here. Let's do the top view free body diagram. What are the forces acting on this astronaut? Get the obvious one. Fooled you. We're in outer space. Don't be putting gravity in now. Okay? So let's be cautious. We are going to be doing some rocket science later on in this unit as well. Let's be cautious. Well, what path is this person tracing out? So where must the net force be pointing? Toward the... So I can at least tell you there has to be a force pointing that way. What force is that? Don't put FC on my diagram. That's going to show up in my equation. What force is that? Push. Huh? Is this person standing on a surface? We have a name for the force that a surface exerts through your feet. Yeah, I think it's going to be the normal force. And that's it in outer space, in a spinning space station. So what's my equation going to be? Who's winning? Who's losing? No one. And that's going to equal MAC. Am I going to use the acceleration equation for circular acceleration that has speed or period in it? How do you know? This time it wants me to find the period. I'm going to get the capital T by itself. So Drake, on the right-hand side, I'm going to go 4 pi squared r over t squared. By the way, this is the equation that kids most often forget to put the mass in front of because that looks so complicated. They think, oh, that has to be a force. It's an acceleration. Now it's a force. On the left-hand side, I have the normal force. I don't know the normal force. Oh, but I know how big I want the normal force to be. How big do I want the normal force to be? %, of gravity, 0.8 mg. If we do build space stations, will little kids and grown-ups be able to feel the gravitational force? Yeah? Why? Okay. By the way, you can see if you forgot to put the m here, you wouldn't cancel out the mass and you'd freak out because I didn't give you a mass. What's this question wanted me to find? Period. I want to get the t by itself. I think what I'm going to do then here, Andy, is times the t squared to the top. I'll get t squared equals 4 pi squared r. I'll move the 0.8 and the g to the bottom. Now that gives me t squared. How do I get rid of a squared? Everybody? Square root. So I want this space station to rotate every how many seconds? 4 pi squared 35 divided by 80% of that 9.8. Again, I strongly encourage you, Robbie, to be typing these into your calculator. Do you have a calculator here? Do you have a phone here? Power it off. Come swap me. So we want this to spin every 13.3 seconds. Now, there's a bit of a problem with this. Ideally, this would work. In reality, even the difference in height between your feet and your head would be enough that your head would feel a slightly different gravity. I suspect you'd feel seasick and throw uppy for quite a while until you got used to it, because there's not a big difference when we add your body to the radius of the Earth. The Earth is so huge, there's not that big a difference in the distance between your head and your feet compared to the center of the Earth. You don't notice that technically there is a difference in gravity between your head and your feet, but it's, negligible. Here, you'd probably notice it. So there's some flaws in this system, but it's a start. B. What's the frequency of rotation? Duncan, isn't frequency just 1 over the period, and period is just 1 over the frequency? Oh, so I can take my answer, which is still on my calculator. Can I show you a new button you may never have used before? You all know you have a reciprocal button, the little x to the negative 1 right there. There you go. All of you have a little x to the negative 1 button somewhere, and what that will do is it will take the reciprocal of your answer. We're going to end up using that later on in circuitry, because in circuitry, for solving parallel circuits, you want the reciprocal quite often. Are you a graphing calculator, Nevada?
Yes.
Right there. Right below the math. X to the negative 1. By the way, this is why, and you've heard me, I think, go on this rant, and I will many times, this is why the symbol for inverse also being a -1 is a stupid symbol for inverse. Because I know this does not mean inverse, this means reciprocal. But that doesn't mean reciprocal of sign, that means inverse of sign. We screwed up as mathematicians. We should have done better. Should have used a Greek letter for inverse. The Greek letter I comes to mind, but we didn't. Do you get 0.0753? And frequency is measured in hertz. That means this thing is spinning with a frequency of 0.0753 hertz. Ready? I wondered if someone would ask. It also tells me a lot of people didn't do all the questions in lesson 1, or the one that talked about hertz, they just wrote down the answer. You ready? Let's suppose that the period of rotation was 30 seconds. Your frequency would be 1/30th. It means you rotate 1/30th of a rotation every second. Let's suppose that your frequency of rotation was 0.5 seconds. That means every second you rotate twice. Your frequency is 2 hertz. Hertz is how many times per second. Period is how many seconds per once. Period is how many times to go around once. Hertz is how many times you'll go around in 1 second. Which is why they're reciprocals of each other, because their units are inverses of each other. We're gonna get to Gravitron. Am I gonna get through all this? We'll see. Yeah, quick look at money, but you're missing cool stuff. Suppose the astronaut begins to climb a ladder that leads to the center of the space station. As he does so, he will feel lighter and lighter. In fact, at the very center, right here, what would he feel for gravity? 0. In fact, if we built mega-sized space stations that were kilometers in radius, the very center would be a very cool recreation area because you would be weightless. You could invent new games. You could put for example, you could go so that you're not quite weightless, not dead center, near center, and maybe where gravity now is like 0.0001, and you could put on a fake pair of wings and fly like a bird because gravity would be so little. It'd be kind of fun. Okay? Or you could put a swimming pool where the gravity is like 0.0005, and it would curve around the axis, the pool would, and in the middle where you would start out, you could put a diving board where you'd be weightless and you would push yourself off from the diving board and slowly drift down until you landed in the pool. All sorts of weird, nerdly, cool stuff could be done. I think we're going to set up the same free body diagram. It's this idea of the normal force equaling MAC. Except this time, what do we want gravity to behave like? What do we want the normal force to mimic? 0.3 mg equals m. Now the advantage with using the period equation, 4 pi squared r over t squared, is your period is the same, the time it takes to go around once is the same on the outside and in the middle. Your velocity changes depending on your radius, but towards the middle, all that means is you're going to spin slower. It'll take you the same amount of time to go around once. So that's how I knew to use this equation. It wasn't because they mentioned period or mentioned velocity. It was because I know here, since I've just changed the radius, the period is what stays the same. What is this question? Oh, doesn't matter whether you're a heavy astronaut or a light astronaut. What does this question want me to get by itself? R equals, I guess, 0.3 g period squared divided by 4 pi squared? Yeah. Hopefully you're also now saying, oh, this is why Dweck emphasized that formula manipulation stuff last. Yeah, to try and memorize every one of these would be just dumb. We can do better. 0.3 times 9.8 times... I got the period sitting right here. Oh, you know what? Actually, I'm going to re-reciprocal, and now I've got the period back again on my calculator because I had the frequency sitting there. So I can go 0.3 times 9.8 times answer button squared divided by bracket 4 pi squared. 13.125, 13.1. If you round it off, you'll get something close to 13 at least. Okay. Just past halfway. Did I say the original radius was 30? Is that what I said? 35. Oh, 35. Okay, so more than halfway up. We already answered D. Nothing. Okay. If you watch the movie The Martian, they do mimic that somewhat in the Hermes, which is the ship that they use to go back and forth from Mars. You'll see the astronauts, when they're along the center axis, are weightless. The only problem is the effects aren't great. It's obvious they're all wearing a harness to float, and then they've just used computers to delete the ropes. Best weightlessness, Apollo 13, because they were actually weightless, right? They chartered the Vomit Comet, and they actually dove into freefall for all of the scenes on board the spaceship. It's why when you watch Apollo 13, when they're on board the Apollo craft, no scene is longer than 19 seconds, because I think they had 21 seconds of weightlessness. So it was action, roll them, and then with 2 seconds left, hit the floor, because you don't want to hit the floor on your, you want to do it ahead of time. Right? I'm going to give you some questions to try already. I'll finish this off tomorrow. I am going to assign number 1 tomorrow, but I haven't done a question like it. I'm going to circle it, but if you can't do it, I'm going to say not answering that yet anyhow. 2 is fair game. 3 is fair game. 4 is fair game. 5 is fair game. 6 is fair game. 7 is good. 8 is good. I'm going to assign 9, the Gravitron, but I haven't yet drawn the free body diagram. That's where we just left off. But has anybody been on the Gravitron? That's the ride where the floor drops away. Yeah. To my shame, I have never been on it. Really? Well, it's not part of Playland. It's part of the P&E, which costs money because I go to the Playland every year with my physics students. I'm really not that interested in going to the P&E. And then I did go to the P&E a couple of summers ago, and it was shut down. Just a little grumpy. 10 is fair game. 11 is fair game. You're giving us lots of questions. Yeah, 12 is fair game. And 12 again. Yeah, there's 2 number 12s. I'll fix that. Oops. I'm not going to do the banked corner, although it's cool. I'm not going to do the banked corner, although it's cool. 16 is good. And I need to show you cool videos, but that's all going to happen next class. If you want to get a head start, though, you should right now be able to handle 2, 3, 4, 5, 6, 7, and 8. Okay?